So here's an example of a hypothesis testing question, which is looking at the means. Using a random sample of n equals 50, the sample mean of x bar is 297.6. And suppose the population standard deviation is 12. Is the above statistical evidence sufficient to make the following claim: that the mean is greater than 295 at the 1% level of significance? The 1% level of significance, or generally the level of significance, is just the value of alpha, the probability of making a type 1 error. And when we get to the end of this question, I'll tell you why we call it the level of significance and if a result is significant. So let's look at the information we're given here. We've got the population. We know that the sample size is 50. And we're told that the mean of that sample, x bar, is 297. 297, actually 0.6. And the population standard deviation, not the sample one, the population one, is 12. And they want us to use a significance level, or a level of alpha of 1%. And the hypothesis they're giving us to check is that the mean is greater than 295. Now, because there's no equals in it, this must be the alternative hypothesis. They're giving us an alternative hypothesis, 295. They're giving us an alternative hypothesis, so this is in fact HA. Now, again, you should have your template available to you, not just during the exam, or your cheat sheet available to you, not just during the exam, but also as you're attempting these questions. The null hypothesis that goes with this is HO, or H0, or H0. They all mean the same thing. That's going to be the mean. Must be less than or equal to 295. 295. And if you look at your cheat sheet or template, you'll see that this is going to be a one-tail test, and the rejection is going to be to the right. Remember, the red alternative points to the right-hand side. So we're going to start off by using the critical value approach. 0 goes in the middle. Now, is this a Z or a T distribution here? Should I put a Z or a T? Well, given that I know the population standard deviation, then it must be a Z. If I did not know the population standard deviation, then it would be a T. We can put the curve on top, we don't have to. And the critical value is going to be over here. And the reject region is going to be to the right. So the reject H0 is going to be from the critical point onwards. Reject H0 region. And the size of that reject H0 region is going to be alpha, or 1%. So this area in here is 1%. And the do not reject region is going to be over here. So again, we always do the test on H0. Do not reject H0. So again, in this problem, we were actually given, the statement we were given that they want us to check is this one in here, which happens to be the alternative. But I'm going to stick to the convention, and I'm going to still be checking the null hypothesis. So I have to come up with the critical value. Now the critical value will be Z, and it will be Z of alpha, not Z of alpha over 2, because it's a one-tailed test. If it was a two-tailed test, it would be Z of alpha over 2. So what is Z of alpha? Z of alpha for this question, well, alpha is equal to 1%, so it's going to be Z of 1%. Basically means the area in here, all in there, that area in there is equal to 1%. So how are we going to actually solve that? We can just pop over to Excel and do it in Excel. So we can use norm. There's more than one way of doing this. So as long as you come up with the right answer, that's all that matters. norm.s dot inverse, and the area to the left of that point, well, if that area there is 1%, the area to the left is 0.99. X always works to the left. So let's pop over and do norm.s.inverse of 0.99 in Excel. So let's see that. Go over to Excel. So we want norm.s.inverse. Norm.s.inverse is 0.99, close parentheses, and that comes to 2.33. Let's go back over to here. So that's going to equal 2.33. Our critical value here is 2.33. Remember, it's a critical value because it's critical. Which side of the test statistic, which is 2.33 right here, which side does the test statistic fall? In the red zone, it's reject. Our answer is reject. In the green zone, it's do not reject. So what's our test statistic for this test? Now, I like to call it the standardized test statistic. You don't have to. You just call it the test statistic. But if you remember, the formula for it is going to be x bar minus the mean. That comes from H0. Now, we already have x bar. We know x bar is 297.6. And the mean that comes from the null hypothesis is just whatever value's in there, which is 295. And we're going to divide that out by sigma over the square root of n. So sigma was 12, n is 50. So let's see what that comes to. X bar is going to be 297. Oops, 297, there you go. 0.6 minus mu of H0 minus 295. And that's going to be divided by the standard deviation, which is 12 over the square root of the sample size, which we said is going to be 50. There you go. Okay, what does that equal to? Let's go over to Excel. See if that can help us out. So I'm going to do it in two stages. I'm going to do the top part, which is going to be 297.6 subtract 295. That's the top part of the numerator. The denominator, the bit underneath, is going to be equal to 12 divided by the square root of, let's see, 50. Okay, so now I have to divide these guys out. So it's going to be 2.6 divided by 1.697, giving me 1.532. So let's come out of this. Let's go to, it's 1.532, go back into here. So the test statistic is equal to 1.532. So where does that fall? Which zone does that fall in? Well, this is 2.33. The 1.532 is going to be less than 2.33, so it's going to be somewhere here. So our conclusion here is do not reject. Our test statistic falls in our do not reject zone, so we look at H0. The test is always done on H0. We do not reject it, so we go with it. But we still get the result for the other one. So the results are going to be opposites. If I agree with one, I disagree with the other. So does the mean appear to be greater than 295? The answer is no. It does not appear to be greater than 295. Now this is an expected result. In the theory, we kind of expect the null hypothesis to hold true. That's what's behind all the theory. We expect it to be true. It certainly doesn't have to be true, but we kind of expect it to be true. So when we, if not on this occasion, but if we end up rejecting the null hypothesis, which we expect to be true, and we go with the alternative, we say that that is a significant result. We weren't expecting that result. So when we talk about a significant result, it means we're rejecting the null hypothesis in favor of the alternative. And if you think about it, in this case, we've got a 99, the area or the probability that we get a do not reject is 99%, and the chances that we get a reject is only 1%. So it's kind of significant if we reject, because it's unlikely, we're not expecting it. There's not much possibility of us rejecting the null hypothesis. So if we do, it's a significant result. Now, again, we solve this right now using the critical value approach. This approach we use right here is the critical value approach. And we're also going to use the p-value approach. So let's do the p-value approach now down here. Now, to do the p-value approach, what do we need? Let's draw it out again. It's going to look somewhat like this. We already know it's a z distribution, and what we need is the test statistic. And we said the test statistic is going to be 1.532. So 0 here. I don't know, just to say it's right here, but it's 1.532. And we need to find out the area for the p-value. The area is going to be the area in this tail here, the closest tail. So it's all this area in here. And to work that out, it's going to be 1 minus norm.s.dist, norm.s.dist of 1.532, the test statistic, and comma 1 or comma true. We can just pop over to Excel and calculate that. This will be the final answer for the p-value. We don't have to multiply it by 2 because this was a one-tailed test. This was a one-tailed test. You can see above it's a one-tailed test. If it happened to be a two-tailed test, this would not be the p-value. We'd have to multiply it by 2 to get the p-value. But let's just pop over to Excel now and find out what the p-value is. So the p-value is going to be equal to 1 minus norm.s.dist. So where is that? Norm.s.dist. And you can either put the 1.532 in here, or you can put the most accurate value in there. You're going to get a slightly different answer, but not by much. And let's see what that gives us. This is the value it gives us. If we want to turn that into percentage, I can just press percentage up here. And I can increase the decimal places, say to 2 decimal places, by pressing this key up here. So it's 6.28%. So let's now go back and say to this here, and we could say that this value is 6.28%. Okay, so now we have alpha for this question. Oops, so just erase that. Alpha for this question is 1%. We were given it, the significance level. The p-value we calculated to be 6.28% is 6.28%. And if you remember to the results from before, we could see right there, before we actually move on, we look at the results from before, we could see that the p-value is greater than alpha. So according to our results before, that implies do not reject H0. do not reject H0. And that's the same as the result we had above. Do not reject H0, do not reject H0, and you get the same result. So remember, like I said, that one way of interpreting the p-value, if the p-value is considered to be large, it's telling you how much agreement you have with the hypothesis, the null hypothesis. So a large p-value is in agreement with the null hypothesis, which means you will not reject the null hypothesis. So what is considered to be a large p-value? A large p-value is any value of, greater than alpha.